Good morning to everyone. I'm Mogli Giorgio, and I'm a PhD student at Politecnico di Torino. And today I'm going to present our research about an highly stretchable organohydrogel used as a strain sensor. What? It's not working. Okay. Now it's working. Yeah. Okay. Let's start with a background. As we know, in several applications like human-machine interfaces, wearables, software electronics, etc., the human world need an effective link with the robotic one. And these two worlds are very different, since the first one is characterized by soft tissues, while the second one is characterized by stiff materials. So tactile sensors, or also called flexible sensors, could fill this gap. Since they are flexible, they are soft, they are conformable to the irregular surfaces of the bodies, they are obviously conductive, and they could respond to multi-stimuli like strains, like temperature, humidity, etc., etc. And one category of materials to build this tactile sensor is represented by hydrogels, which are a polymeric network that could retain a huge amount of water, and so are intrinsically soft, and they have obviously mechanical and electrical properties that can be easily tuned. So our work is based on the development of a 3D printable hydrogels that could be 3D printed through digital light processing technique. The hydrogel is composed by obviously water, in which ionic conductivity is achieved through the dissolution of sodium chloride. The hydrogel is composed by a soft network based on polyvinyl alcohol, interpenetrated with an hard network of acrylic acid, which is cross-linked by polyethylene glycol deacrylate. The two acrylate species react to UV lights, and so 3D printing was possible. And so the photoinitiator, water-soluble photoinitiator, was dissolved into the precursor formation. The yellow color is given by a water-soluble dye, tartrazine, which was added to improve the resolution of the printing. But the main drawback of these hydrogels were conductive and stretchable. But the main drawback of this hydrogel is that water evaporates. So the resistance, electrical resistance, is not stable a long time. So the idea was to substitute part of water with an organic solvent, an high boiling point solvent like glycerol, to obtain an organohydrogel. So the 3D printed hydrogels were immersed, exploiting a solvent replacement strategy, into a binary solution of water and glycerol, in which also 1 molar of sodium chloride was dissolved. And first of all, a weight analysis was performed to assess how the hydrogels changed. And in the first few hours, the weight of the samples decreased because the water exited from the polymeric network. Then, after 2 hours, the weight started to increase, reaching an equilibrium after 5 days of immersion, more or less. So these 3 immersion time were considered for the further analysis. The 2 hours because corresponds to the minimum amount of solvent, binary solvent entered into the network, and the 5 days and the 10 days immersed samples because they are at equilibrium conditions. Then, since this organohydrogel is thought as a strain sensors, tensile electromechanical tests were carried out, and the Young modulus and gauge factor in the first linear range of the response of the sensor were evaluated. As regards the Young modulus, as we can see, the 2 hours organohydrogel have not stable Young modulus, since their stiffness starts to increase after 10 days of testing, and then so they were excluded from the study. On the other hand, the 2 other hydrogels taken into account show both mechanical and electrical stable properties along 2 months of study. So the 5-day samples were taken into account, since they take less time to build them. And a tensile test up to rupture was conducted, showing an optimal stretchability. They were able to elongate up to 450% strain. And they showed a linear piezoresistive response, because when the hydrogel is stretched, the ions need to cross a longer path to cross one electrode from the others. So this is the red one is the piezoresistive positive curve, which show three linear range in which the gauge factor could be computed, and is similar to the others found in literature that regards the ionically conductive hydrogels. Then cyclic tensile tests were carried out to evaluate the reflectability of the measures, and here we can see the comparison between the cyclic test conducted on the organohydrogel and that conducted on the pristine hydrogels. And this result showed that the organohydrogel has lower hysteresis and so lower drift and allow more repeatable measures. Then, since the precursor hydrogel was 3D printable, 3D structures were evaluated in pressure test by applying a small weight on the top of these structures. The two structures that were 3D printed was the bulk one and the stars one. And as we can see from this graph, the relative variation resistance of the star structures are higher with respect to the one of the bulk structures, showing that the 3D printing could be a promising tool to enhance sensitivity of the sensors. Then a complex analysis was carried out. This analysis is called dynamic mechanical thermal analysis, DMTA, which is an analysis in which the Young's modulus of the samples, which are clamped into in this manner, is evaluated while the temperature is changed. This machine allows to apply small strain to the samples, and the samples are maintained in a closed chamber with controlled temperature. So the idea was to couple this measure with an electrical measure by applying two electrodes to the samples. And it was found this graph in which we can see that the Young modulus at the black line obviously decreased when the temperature increased because the mobility of the polymeric chains increased, and the resistance, which is the blue line, which can we see from this zoom, it is responsive to the external cyclic strain applied. This resistance decreased while temperature increased because the ionic mobility is enhanced. And moreover, the relative variation of resistance, which respect to each cycles, were computed and were reported in the red line. And as we can see, they decreased when temperature increased, since the ionic mobility at higher temperature is less affected by external strain. So the sensors are less sensitive to external deformations. Then, since the instrument allow us to apply small strains at various frequencies, were evaluated several strains, very small strains, at various frequencies, showing here the resistance path are reported. And as we can see from this zoom, the minimum strain detectable from this organohydrogel sensor was 0.05%, in which we can see in this curve, the blue light curve, we can see the cyclic deformations which are reflected by the resistance cyclic fluctuations. And moreover, the average values of the variation of the resistance for each frequency of the deformation applied were computed, showing that for each deformation investigated, they are quite stable. So to sum up, I presented the ionically conductive organohydrogel with a long-term stability, which could be used both at strain sensors or pressure sensor and temperature sensor, which can be 3D printed to enhance its sensitivity to external deformations, and it is able to detect small deformations at various application frequencies. So at the end, I would like to thank all my collaborators and you all for your attention.